In the previous video, I talked about aqueous dissociation equations for acids and bases. And we talked about equilibrium constants and acid and base dissociation constants and electrolytes. And now I want to take a look at some specific examples of, in this video, aqueous acid dissociations. And then in the next video, aqueous base dissociation equations. The key here, and I think if we can pull out one overshadowing idea in writing these aqueous acid dissociation equations, is take an H off, all right? When you're writing an aqueous acid dissociation problem, your job is to remove an H. So if we start with something simple, and we're going to have the basic things I'm going to be looking for here. We're going to write the aqueous dissociation equation. We're going to write a K expression. And we're going to label our conjugates. So those are the things I'm going to be looking for and trying to accomplish here. The first example, we'll pick something simple, and that is HF, hydrofluoric acid. So if you're asked for an aqueous dissociation equation, every single time it's going to be whatever you have for an acid here, plus water, right? Aqueous means in water. And that'll be a liquid for these purposes. We have the double arrow indicating an equilibrium system, and if this is an acid, it's going to lose an acid. Sorry, if this is an acid, this is going to lose an H. That's it. That's the part we need to remember. That's a new orange marker and it didn't work so well. You're going to remove H1, all right? And that's H plus to be clear. So let's take a look here. HF is going to turn into F minus, and the H is going to go to water, and we're going to get H3O plus. Recurring theme, right? So this is going to give us H3O plus and F minus. When we're writing our K expression, we set it up as products over reactants to their coefficient powers, and water's not going to come into play. So in this case, H3O plus F minus over HF. And those brackets from other videos you may have seen, that represents concentration, a molarity in this case. So that's read as concentration of H3O plus. We don't put the water in there because it's a pure substance, right? So that's the most common question I had mentioned in the previous video. Products to their coefficient powers, reactants to their coefficient powers, but not liquids or solids in an equilibrium system. This happens to have a value that we can pull out of a table of acid dissociation constants, Ka values. I have a table like this. Obviously, print's too small to read, but that's fine. This number here happens to be 7.2 times 10 to the minus 4. And that tells us that HF, hydrofluoric acid, is a weak acid. Okay? And if you remember the previous video, we said weak means it's going to have a numerical value. Strong acids and bases, strong electrolytes, have large K values. And what we mean by that is literally the word large. And you'll see that in subsequent examples here. So this is a weak acid. All right, we have a number, so we're going to consider that a weak acid. In identifying conjugates, as we look this way, we just determine how things changed. HF turned into F minus by removing an H. It lost an H, and things that lose H's we call acids. H2O, as we look in that direction, turned into H3O plus, and it did that by accepting a proton from our acid. Things that accept protons we call bases, right? And then to figure out what our conjugates are, we're going to look in that direction. And I'll say F minus, what does that turn into? Well, it turns into HF, and it does that by accepting a proton. And things that accept protons we call bases, but it's on this side, so we'll call it a conjugate base. Correspondingly, H3O plus, looking that way, turns into H2O, and it does that by losing a proton, losing an H. Things that give up protons are acids, and then when it's on this side, we call it a conjugate. All right, I'll abbreviate those in later examples, but for right now, that's what we're looking for these acid-base equilibrium systems. Eventually, we're going to take this and set up equilibrium problems with it, ice problems, but for right now, our task, our skill is just writing these out, and this is going to be the key idea, just take an H off as things get more or less complicated. Let's look at a second example here, a common acid and another binary acid with a halogen, and that is HCl, right? Hydrochloric acid. So the problem in the book, or whatever might say, write an aqueous dissociation equation for HCl. So we've got HCl aqueous. It's going to be an H2O every single time. You're going to have some acid plus H2O goes to the hydronium ion plus the conjugate of that acid. And it's worth noting, it doesn't matter whether you put F minus and H3O plus or H3O plus and F minus. So the additive property, like 2 plus 3 is 5, and 3 plus 2 is 5. It's been a long day. So as we look at this, we'll end up with H3O plus again, and that's going to be aqueous, and our Cl minus, and that's going to be aqueous. It looks very similar, as it should. They're both binary acids. The Ka expressions are also going to look very, very similar. We've got H3O plus, and we've got the halogen Cl minus over HCl. And again, we're not going to include the water in that equilibrium expression, pure substance. This, if we look at our K table, has a K value that is large. Okay, so we mentioned in the previous video, what does it mean? Like when we say strong electrolytes have large K values, we literally mean the word large. If you look at the table, it says large. So that's how we know. This is what makes it, or this is how we identify it as a strong acid. Okay? And that's the basics of that. So what happens if you have some polyprotic acid? Well, we'll take care of those later, but for right now, let's worry about like oxyacids, or things that have polyatomic ions. And we'll start with maybe nitric acid, HNO3, and that's aqueous. Again, not really much more complicated. We have a polyatomic ion this time, and we're still going to have plus H2O, and that's going to give us H3O plus again, because that's what acids do. And now we're going to get what's left. So I don't necessarily think it's much of a trap or much of a trick to watch out for. The nitrate polyatomic ion is our conjugate. And there's some really neat stuff later in the acid and base videos, if I get to one, that talks about like the acid-base nature of salts. Like nitrate is the conjugate of a strong acid, so it's neutral. And I kind of wrote down some of that information in the previous video. The Ka for nitric acid, H3O plus, that sounds familiar. NO3 minus, the nitrate polyatomic ion, and we got HNO3, same deal. No water in there. The K value here happens to be large. Okay, what does that mean? It means that nitric acid is a strong acid. Okay, and when we say large, we literally mean the word. That's this constant point of confusion. All right, so we'll look at one more example here before I erase, and then we can pick up the rest of our examples. A very similar looking acid, but not the same acid, is nitrous acid, HNO2. All right. The idea, take an H off. All right, I have an H, I'll take it off of there. We've got H2O for our liquid. This needs to lose an H. Okay, we get H3O plus. And we get whatever's left, and that in this case is the NO2 minus. Our Ka, in this case, we've still got H3O plus in NO2 minus over HNO2. Now, if you know a little bit in advance about these acids, nitric acid strong, nitrous acid not strong. In fact, it has a K value of 4.5 times 10 to the minus 4. Okay? 4.5 times 10 to the minus 4. If you remember the previous video, we're looking at weak as being K values between 0 and 1, or significantly less than 1 in most cases. All right, so in this case, this number here implies that this is a weak acid. And we didn't label this before, but I said I would, so we should go back. This donates a proton to become Cl minus, that's got to be our acid. This accepts a proton to become H3O plus, that's got to be our base. In the reverse direction, H3O plus turns into H2O by donating a proton. That's an acid, and when it's on this side, it's a conjugate acid, right? Cl minus accepts a proton to become HCl. That is a base that accepts protons. When it's on this side, we call it a conjugate base, all right? Because of my lack of foresight, H3O plus, H2O, H3O plus, those all end up our conjugate acid, all right? And those all end up our conjugate base. That's not because the first thing is always the conjugate acid and the second thing is always the conjugate base. It's just because I'm a creature of habit, all right? Acid, base, and here we have H2O acting as a base. When we looked at the base dissociations last time, we saw H2O acting as an acid because it's amphoteric, right? And we'll get into that vocabulary term in another video. All right, that is that. Those are simple aqueous dissociations. Now look at things that are a bit scarier, but not a big deal, okay? Once we know this trick, the idea that you're just going to remove a hydrogen ion then even the scariest ones become less scary. And let's start with something that I use as an example all the time, acetic acid. And the reason I always choose acetic acid is it's like super relevant in your day-to-day lives. Acetic acid, like a 3% solution of acetic acid, is vinegar. All right. So acetic acid is CH3COOH, okay, or COOH. Yes, you could write it as C2H3O2H with the acetate polyatomic ion, but I think that in the big picture, this tells us the structure. So very commonly people say, why do you write it like that? Why don't you combine it? Well, this is telling us, and I'll write it this once, but this tells us carbon has 3 hydrogens. Carbon, hydrogen, 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 right? And that's attached to another carbon that has an oxygen and an oxygen. And that oxygen has a hydrogen. And that hydrogen right there is the acidic hydrogen, the hydrogen that can come off of there. This acetic acid is a type of carboxylic acid. So why write it out CH3COOH? Well, because CH3COOH. That's why. Instead of writing it C2H3O2 or something. It's fine. It means the same thing, but it gives us a little more of the structure picture as well. All right. Aqueous dissociation equation. Every time something plus H2O. If it's an acid dissociation equation, then this has to lose an H. The question that always comes up, which H? And the answer is the one on the end. All right. If you've got the option, it's the one on the end. So we're going to get H3O plus because that water is going to act as our base, and we're going to get whatever's left after we take that H off. CH3COO minus the acetate polyatomic ion. Conjugate acids don't have to have a positive charge. Conjugate bases don't have to have a negative charge. But if we're starting with something neutral and something neutral, for acid dissociations, that's going to happen. Our Ka in this case, I need a little more room. We've got H3O plus and CHCO. And in the bottom, I've got CHCOH. One of my kids a long time ago, instead of saying acetate or CH3COO, CHCO or CHCOH. I'm sure they're not the first one to have come up with that, but I think it's funny and I keep using it. In this case, the Ka value for acetic acid is 1.8 times 10 to the minus 5th. All right? What is the significance of that? That means that acetic acid is a weak acid. It does not dissociate completely in solution. All right? So this is what's telling us that we have a weak acid. All right? That is acetic acid. Once again, the idea is, which H do I take off? Hopefully one on the end. And how do I know what to do? Take an H off. It's those two key steps. And here's where things might get a little more scary, right? We need to go back to our roots. When in doubt, just take an H off. So say we've got something that looks a little more frightening, like an amine CH3, NH3 plus, yeah? And that's going to be aqueous. This tells us what we have to do, an aqueous acid dissociation. So we know it has to be plus H2O. And then this has to give up an H. And I'm going to have H3O plus. And when this gives up an H, all I need to do is write this with one fewer H. So that, in this case, is going to be CH3NH. And we lost an H plus, so our charge has to drop by 1. CH3NH2. Okay? So we lost an H plus. Now I have 2 H's, and I lost a plus, so it ends up neutral. All right? And our Ka for this is H3O plus, CH3NH2, CH3NH3 plus. And the value for this is 2.3 times 10 to the minus 11th. All right? And again, that just comes from a table somewhere. And the significance of that is this is also a weak acid. If it weren't a weak acid, the K value would be large. And again, what that means is literally it says the word large. The last one I want to look at as we're working our way up the terror scale is this. And I'm going to maybe set it up in a different color so it pops out of the board a little bit. And that is something like the hexaaquyl iron 3, which is a complex ion, but Fe, H2O, 6, 3 plus. You have tools in place to do this, and the tools are, if it says it's an aqueous dissociation, then you have to remove an H. Okay? It's going to be whatever you have plus H2O and remove an H. I know I keep saying that, but that's all there is to it. That's your strategy. So I need to remove an H from this. Well, I have 6 waters. If I take one H away, that's only going to affect one of those waters. So 5 of those waters aren't going to change. And I'll say that again in slow-mo. I have 6 waters. I need one H. Not one H from each of them, just one H. And so one of my waters is going to change. 5 of them are going to stay the same. So we've got our H3O plus because water gained that proton. And then we have what is left of this, which is Fe. 5 of the waters didn't change. And one of the waters lost a hydrogen. So what's left there is an OH, right? And then our charge, since I lost an H plus, becomes a 2 plus, and that is aqueous. So once again in slow-mo, one of the waters changed, it lost an H plus, that left an OH, 5 of the waters remained unchanged, and then I don't have a 3 plus anymore because I lost an H plus, now I have a 2 plus. And my Ka expression for this is going to be this, which is somewhat annoying to write. Every time I do one of these problems, I regret it when it comes to writing the K expression. And we have those concentrations. The K value for this happens to be 3.2 times 10 to the minus 10, which indicates that, again, we have a weak acid. So that's some examples of aqueous dissociations for common acids, or not so much. And the key is take an H off. Regardless of what it is, plus H2O gives you H3O plus, and then something without an H. And if you can, or if you don't know, just take an H off the end.